Good morning. My name is Hilbert Muchatibaya from Rhodes University, and I'll be doing a presentation on my paper titled A Review of the Siyakhula Living Labs Network Solution for Internet in Poor Communities. We'll start with the terms and the definitions that will be used throughout the paper. The main terms are two, which is Siyakhula Living Lab and digital access nodes. Siyakhula Living Lab is a long-term experiment in connecting the unconnected and has been conducting research into providing sustainable off-the-shelf infrastructure for rural communities in South Africa. Digital access node is the point of presence or an access point in the network solution. The Living Lab methodology is a hybrid approach to implementing ICT-40 projects, where instead of taking the traditional top-down approach, with the Siyakhula Living Lab approach, it's user-driven. So that means that we work closely with people in the communities to provide solutions to their day-to-day problems, and to also ensure that we get buy-in from important stakeholders from the communities when we are providing a project for them. Next is the geographic layout of the broken islands. So as you can see, we have three nodes, one in Ngwane, one in Badi, and the other one is in Mpume. The main two nodes, the digital access nodes, as explained in the previous slide, are where the schools and the people in the community access the network. So that's where they can get access to the network and either communicate with other people or schools within the network, or make a request to the internet. And for them to go to the internet, we have the three satellites that are there. Bear in mind that this is what the broken islands look like in our first iteration or our first implementation. And as we review that, we will propose updates in technologies and changes where it's necessary. Methodology. So we're going to be doing experiments. We did experiments in the form of engaging the community directly, lab experiment to simulate live deployment, reflection on the results post-deployment. So this, in essence, is what describes the Living Lab methodology. It's a iterative process in which we work closely with people, the stakeholders or the beneficiaries, which are in this case the villagers or the community members, and we work out a solution that meets the context. We see whether that solution is ideal. Where we fail, we take note and we repeat the process again, and we do an improvement. So this paper in itself is an iteration. It's another iteration where we go through mistakes from the past and we see how we can improve it and see if our solution implemented 10 years ago is still viable in recent times. Motivation and the problem area. Within ICT over the past decade, changes within ICT over the past decade have required us to review the Siyakhula Living Lab proposed solution to see if it can be improved. So this means that we're reviewing the network solution deployed in Siyakhula Living Labs, investigating alternatives to caching with the rise of HTTPS traffic on the web, solving the issue of page width and unwanted ads that use up too much bandwidth, and proposing a scalable implementation approach that can be adopted by the government moving forward. So here's a review of the network implementation. One of the decisions that we had to make was to decide whether, because many technologies could have been used to implement this blueprint. We could have used optical fiber, we could have used satellite, we could have used WiMAX or Wi-Fi. So in this instance, wireless technologies fare better where they are predominantly low-income households and the population is generally dispersed. The reason for this is that there is a low initial cost of investment when you're setting up wireless technologies. They do not require highly skilled or specialized workers. It's something that is the skill needed to set up wireless technologies in rural communities, particularly, are very easy, like very entry level, and are very transferable. And due to the mass production of wireless devices and more sophisticated antennas, the wireless industry has made dramatic advances in terms of throughput and reliability. It is worth noting that fiber connectivity has gained some momentum in South Africa townships over the past 10 years. In 2019, Gauteng MEC promised free internet services to townships in the province. The growing movement to connect townships with fiber has already given rise to competitive pricing. For example, Vumatel announced a project to provide internet speeds of up to 100 megabits per second for less than 100 rands per month in an Alexandra township. Therefore, the choice to use wireless technology in real-world implementation still makes sense. So this means that going forward, based on this review of the network implementation, we will still maintain that wireless technologies are the better option. As for specific technology, we're using WiMAX initially. However, it is no longer supported by the market, and I will get into more details about that. So, as for the specific wireless technology, WiMAX seemed very promising in 2005 for the land portion of the broadband island, but GSM was quickly becoming the dominant mobile wireless standard worldwide. Therefore, the next natural progression for market to 4G was through LTE instead of WiMAX because it provided a much easier upgrade for their GSM, UMTS, and HSPA-based networks and subscribers. The long-distance Wi-Fi is the obvious replacement for fixed wireless niche for which WiMAX was created initially. As WiMAX, Wi-Fi has the important characteristics of being a technology easy to deploy physically with only basic skills and without requiring investments beyond the capabilities of micro and small enterprise. Broadband Islands with Wi-Fi maintains the important characteristics of the initial WiMAX installation to be a grassroots technology. The preferred backhaul solution might often be Wi-Fi backhaul to points of presence of government-run national fiber network, which should exist as part of the SA Connect broadband plan. Reviewing caching and reducing data usage within the network. A field experiment in Ghana reviewed that the data consumption was very high and not sustainable in the long run. Further experimentation reviewed that our cache was no longer effective because of the advent of HTTPS. With the growing concern of network security and privacy, a large portion of the internet traffic is now encrypted. Recent research indicates that over 70% of web traffic is now being transferred over HTTPS. According to HTTP Archive, from 2015 to 2020, there has been an 18.1% and 47% increase in image sizes used in web pages on desktop and mobile devices, respectively. Web performance has also been impacted, for example, by scripts running in the background to load and display unwanted ads. To address the problems mentioned in the previous slide, we used Squid SSL bump, pick, and splice feature to allow caching of encrypted web pages. Installed PyO, a DNS sync for ads to remove the ads. These two solutions both deal with separate issues within the network, but ultimately contribute to the bigger goal: reduce data usage. In addition, we built an external component, i.e. a browser extension, to work in unison with Squid and PyO. This browser extension has use cases beyond the Siyakhula Living Lab network solution. Now I'll give a brief explanation of the Squid feature mentioned earlier, this SSL bump, pick, and splice. Squid, so what happens now is Squid inspects the authentication messages between the client and the server during the TCP and the TLS handshakes. and then duplicates them to mimic the server to the client and vice versa. Essentially, Squid becomes the man in the middle for the authentication process between the client and the server. However, both the client and the server are unaware. This ability to mimic both the client and the server is the cornerstone of this feature, because we still retain our ability to use end-to-end authentication while leveraging the benefits of an in-network proxy cache. However, for security reasons, we do not filter traffic going to sites that contain sensitive client data. To do this, we create a blacklist, which is a list of websites that will not be filtered based on how sensitive the information is. And in our situation, that is a better trade-off, given the fact that the overarching issue here is the digital divide. And within the digital divide, financial viability is a constraint. And the trade-off here is, instead of having full privacy and leveraging the maximum benefits of encrypted traffic and HTTPS, we risk introducing security issues in the hopes of, with the pursuit of saving more data in the process. So if our cache is effective, which is an integral part of the model, it means that we can save more data and our network can be more efficient, and we also limit bandwidth usage on the uplink or on the link to the internet. Pi-hole, a DNS single for ads. Pi-hole is a network ad blocker which acts as a DNS single and is intended for use on a private network. A DNS single is used to provide false DNS information to systems and can allow attackers to redirect users to a malicious destination. So that's the general description of what DNS single is except for us in this case now, what is redirecting are the ads, so that you do not have to download excessive ads and use up too much data. However, ads generate revenue for website owners. As a result, they block users from viewing their content if they have an ad blocker. And Firewall can circumvent this by blocking ads at the network level. These website owners put bait content on the website that's the ad that they can look for each time someone loads the page. So if they do not see a certain div tag, for example, that they put there as bait because it's been blocked by an ad, they can tell that you're using an ad blocker, and therefore they can block you from viewing the content for free. So what Firewall does now is, it's, instead of blocking the div elements from actually being loaded, it just blocks the ad from being fetched on the network level. So to the client, or to the website owners rather, it appears as if it's a network issue and not that the client has actually blocked the ad, therefore allowing us to circumvent the pushback that we get from website owners. It is quick and easy to install. You just run a single command, and it can be installed because it is installed at a network level. In this case, we can put it on a server that serves all the whole network, and we can only have one instance of it. And it's then, for that reason, it scales better, because we don't have to install it individually on each machine. It can simply be installed on our server, on one main server, and distributed across the network. Our image blocker extension. The browser extension blocks all images from being downloaded over the network. It allows you to pick the images I want to view and download based on that. Usability experiments were performed in the lab, and we concluded that removing images while browsing is a better trade-off, given that the goal is to minimize bandwidth consumption. And as for the results, the cache hit rates went from 0 to being between 20% and 80%. According to the diagram above, ads constitutes roughly 50% of traffic, and by blocking them, we save that amount of data highlighted in green. The image blocker extension, with the image blocker extension, we managed to save at least 50% of data the website. In conclusion, this paper reviewed the SA Connect plan and the blueprint for ICT networks deployed in poor communities within the Siyakhula Living Lab over years, and suggested technological updates where it was necessary. The review blueprint might hopefully become a component of a revised blueprint plan by the government, the SA Connect. The SA Connect plan has not been a great success, and the fundamental reason behind it is the design and deployment of ICT projects are context-sensitive endeavors, and because it takes a traditional top-down approach, as I mentioned earlier, the implementers missed important aspects that come with different environments. The blueprint of the network component of the Siyakhula Living Lab built through the Living Lab methodology should be considered in the SA Connect plan.